I want you to recall what we discussed earlier in this chapter about solubility. Realize that anytime we have a solid that has to go into a liquid solvent to generate a solution, there is only a fixed amount that can, or a maximum amount that can be dissolved per unit of solvent, and that is what we say is called as the saturated solution, or the saturated, that is the concentration at which maximum amount of solute has been dissolved in the solvent. So in that sense, if you think about it, the dissolution of a solute in a solvent is sort of like an equilibrium process, similar to the phase changes that we discussed in chapter 11. Because, from a molecular viewpoint, you can perhaps see that if you have sodium chloride, that's the simplest to discuss. If you have sodium chloride and you put water into it, okay, when you do this, you would see initially water molecules will begin to solvate both sodium and chloride. They're going to dissociate, and you're going to end up with Na plus and Cl minus, and then this Na tends to interact with the water molecules, and hence we say that the solvation takes place. And so realize that in this process, as sodium chloride, which originally was in the sodium chloride solid form, as it begins to form Na plus and a Cl minus, essentially one would see that all of a sudden the amount of solid NaCl that was present has decreased. And when that happens, then the solution all of a sudden becomes more concentrated, and with respect to the sodium and the chloride. And at that point of time, maybe if the concentration is more than that a saturated solution can hold for that particular temperature, maybe some of the sodium and chloride will come together and they will start crystallizing the sodium chloride solid back. So in that sense, it's similar to a forward and a backward process, which is why I'm using the word equilibrium to show you that. So again, what I really want you to understand is that a solution in which the dissolved solute is in this dynamic equilibrium. That means the solution cannot hold any more solid. This is what is called as the saturated solution. And if you add any additional solute to a saturated solution, it's not going to dissolve. A solution containing less than this amount is what is going to be called as an unsaturated solution. So if you continue to add additional solute, of course, that's going to dissolve. And under some certain circumstances, we can generate a supersaturated solution which contains more than this equilibrium amount, but then such solutions are unstable, and any additional amount essentially precipitates out of the solution, and essentially, if left undisturbed, this can exist for an extended period of time. So and of course, we have discussed all of that before. Now, there is another term that we often use, which is called as miscible, and this is usually used for liquids and liquids in liquids in general. And that is used for liquids that are mutually soluble in all proportions. A great example would be, ethanol and water. In a lot of proportions, those are soluble. And so a lot of times we will use the word miscible. As far as solids and liquids go, in general, the effect of the temperature on solubility is that most solid substances will become more soluble as the temperature rises. However, if your solute is a gas, it will tend to become less soluble as the temperature rises. This is by far one of the reasons why, if you have a soda pop and you open the can and you drink whatever you want to, and you did not finish it off, and so you just left it at room temperature, it's going to go flat very quickly. On the other hand, if you store it in the refrigerator, in that case, the the soda pop will remain, it will have that zing to it for an extended period of time. So realize that gases, they have a tendency to become less soluble as the temperature rises. Going back to the solids, the solubility of solids, as far as temperature goes, recall since we discussed that earlier. Essentially, if you increase the temperature, you're forcing the volume of the solvent to expand a bit. That means if you had, let's say, something like water molecules, and you have molecules, let's say, at that distance. By increasing the temperature, you're going to increase the volume. So now molecules are going to be far apart. And so you have created more space where the solute particles can go in. And that is the reason why, as you increase the temperature, solids will have a tendency to dissolve more. But anyway, going back to the gases that I was discussing, which is now the time that we are going to the point that we are going to go over. Like I said, club soda or soda pop, it goes flat very quickly, and the reason for that is the decreased solubility of carbon dioxide in the solution. Another example could be the dependence of fish on the oxygen that is dissolved in the lake or the seawater, or the fact that our blood contains dissolved nitrogen and oxygen and CO2. And so when we breathe, essentially it's an exchange, of gases that's going on. Even the tap water that you get, that has dissolved gases. So the one thing that I would want to say here is that for the case of gases, both the temperature as well as the pressure play a fairly important role in the solubility. For the case of solids and liquids, the temperature plays a vital role, the pressure not so much. Okay, so just what I discussed. The pressure doesn't quite have as high an effect on the solubility of liquids or solids. However, it does affect the solubility of gases. Essentially, higher the pressure of the gas above the liquid, more soluble that gas would be in the liquid. So, for example, in case of the soda pop that we have been talking about, that we have been discussing, you have the liquid and then there's this little space before which they seal it. And so CO2 is maintained in the solution by having a high pressure of carbon dioxide within the can. So when you open the can, essentially you hear the tush sound as the pressure is released, and the solubility of the CO2 would then start decreasing because of this. All of a sudden, the decrease in pressure has taken place, and so now CO2 will start bubbling out of the solution. You can perhaps envision that when you have the soda can, and here is where the solution is, and here is where the additional CO2 is, and here is the CO2 that is dissolved in that solution. So because we are maintaining this additional pressure, essentially, there is an equilibrium that is set up between the gaseous and the dissolved CO2. So there's an equilibrium between the CO2 gas and the dissolved CO2 within that solution, such that the rate at which the carbon dioxide molecules enter the solution exactly equals the rate at which the molecules are leaving. So there is an equilibrium that is set up in the system. Now, if you decrease the volume, so if you bring this, you are increasing the pressure, you're lowering the volume, so greater amount of pressure. What would that mean? That means that you're forcing more number of CO2 molecules to go into the solution phase, and as the number of molecules in the solution increase until that equilibrium gets established. So overall, you would see that the amount of CO2 now in that solution is going to be greater. So one can say that the solubility is proportional to the pressure of 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 that particular gas. The solubility is essentially measured in molarity or moles per liter, and the pressure that we are talking about is pertaining a specific gas, so you can call it the partial pressure as well. Partial pressure. And usually the units will be in ATM, atmosphere. So now if you remove the sign of proportionality, you have to introduce a constant of proportionality, which in this case is called as Henry's constant. And this law, this relationship, that solubility is a function of partial pressure of that gas, is also called as the Henry's law. Okay, this slide kind of talks about what we just discussed. The first picture shows you the case of that soda pop I was talking about, where you have a gas, let's say CO2 is my gas, and that was present on top of this liquid. So there is an equilibrium that is set up between the gas on top of the liquid and the gas that is dissolved in the liquid. Now, if you increase the pressure, that means you're going to force more and more CO2 molecules to be dissolved in that liquid. And this will continue to happen until a new equilibrium is set up, such as the one shown in C. So for this to occur, again, we can say that solubility is a function of the partial pressure of that particular gas, and so S is equal to K P, where this is in moles per liter and the pressure is in ATM. So one can say that the units of K are going to be moles per liter per atmosphere. Okay, question this hour is, which of the following will become less soluble in water as the temperature is increased? So hopefully you can see less soluble in water. That means it has to be a gas. It's got to be CO2. NaOH being a solid is going to only dissolve more as you increase the temperature. Okay, let's go forward. The question is, the solubility of CO2 in water is 3.2 times 10 to the negative 2 molar at 25 degrees Celsius and 1 atm pressure. What is the Henry's law constant for CO2 in moles per liter per atmosphere? Now realize, since we are maintaining the pressure of air, that is going to be the partial pressure that is provided for this will be 1. Solubility is 3.2 times 10 to the negative 2. So simply you can simply, this is a plug and chug type of a question, negative 2 moles per liter per atmosphere is going to be the value of K. Okay, let's discuss colligative properties. Colligative properties are those properties that basically depend on the amount of the dissolved solute, or rather I should say the number of particles. The number of particles. So how many number of particles are present, but not the chemical identity of it. So it doesn't matter what you dissolved, whether you used KCl, NaCl, or whatever it is that you used, but rather the total number of active particles that they decide the overall effect on some properties, and such properties are what are called as colligative properties. There are basically 4 main colligative properties: the lowering of vapor pressure, the depression of freezing point, the elevation of boiling point, and osmotic pressure. We are going to discuss all 4 of these, and like I said, the lab that we are going to run next week, that's going to be based on the freezing point depression. Essentially, this section of this chapter answers questions like, why is it that if we have to prepare ice cream in an ice cream maker and we put in the ice for that, for the cooling purposes, we add salt to it? Or during the cold winter time, if you have ever lived in the northern states, you would know this, that they scatter salt on icy roads. We don't have to do that in Florida, but why do we have to do that? The answer to that is that salt essentially lowers the temperature at which the salt water solution freezes. And so salt and water solution that will basically remain a liquid even below 0 degrees Celsius. And so and the same thing in case of the ice cream maker. When salt is added to ice in the ice cream maker, this mixture essentially forms that gets formed. It can reach temperatures of, as low as like -10, uh, and that is the point of time where ice cream freezes. So of course, you can see that the presence of the salt is doing something to the freezing point of water. So that's what we are going to discuss, how it gets affected. Now, before I discuss the little details of each of these, I want you to understand that in comparison to the properties of a pure solvent, when you compare those to a solution, so realize in case of a pure solvent, you have only one kind of particles. In case of a solution, you have the same solvent, plus now in addition to that you have some additional particles. So the vapor pressure of the solution is lower, the boiling point is higher, the freezing point is lower, and we'll also talk about osmosis, how it affects the osmotic pressure across the membrane. Okay, let's get started. So let's say you have a sample, you have a liquid, okay, and it's a pure solvent, it's a pure solvent, it's a pure liquid, and you have, it's a closed container also, you have molecules within it. So some molecules get into the vapor phase, right? And you can measure, you can connect it to a manometer, and you can perhaps measure the vapor pressure due to the vapors that are present on top of this liquid. Now, if you compare that to another situation where you have the same liquid, but now you have mixed in that liquid some kind of a non-volatile solute. Non-volatile solute. What do I mean by that? Non-volatile solute means that the vapor pressure of that particular component is going to be pretty low. So what's going to happen if you envision the top layer here? Since it contains some non-volatile solute, some of these, and I'm going to just change the color for just a second. Maybe this is a non-volatile, this is a non-volatile, maybe another one is a non-volatile solute. What does that mean? That means that when the solvent is ready to, get converted into the vapor phase, since the top layer does not quite contain all of those positions, are not taken up by that volatile component, essentially the vapor pressure is going to be lesser as compared to the vapor pressure when it was completely pure. So one can say that the vapor pressure of the solution, this is my solution, that is going to be lesser, lower than the vapor pressure of the pure solvent. And if that is true, then one can just suggest that basically the non-volatile solute that we have added, that is able to interfere the ability of the solvent particles to vaporize, because of course they are going to occupy some of these positions. Now, another way to view that is that the rate of vaporization of the solvent is going to diminish as compared to the pure solvent, again because of the presence of this non-volatile solute. So this is going to essentially create some sort of a imbalance in the rates of the vaporization and the rates of condensation between the two scenario. Now, you can perhaps even envision that if you have a closed container in which you have the pure solvent and you have another beaker which contains a concentrated solution, essentially due to the difference of the vapor pressure between the two, essentially the vapor pressure of the volatile liquid being higher, the level of the liquid is going to drop in case of the pure solvent, and it's going to go deposit essentially with the solution, which is where the level of that solution it's going to rise. What I also want to say here that if the solute is volatile, that means it itself has a significant vapor pressure, then the vapor pressure of the mixture is going to be intermediate between the two vapor pressures. What I mean by that is, let's say you have a combination between water and ethanol. Water, suppose the vapor pressure of that is maybe 100 millimeter mercury. I'm just coming up with some number. Ethanol is more volatile, so vapor pressure will be higher. Maybe that's 200 millimeter ethanol. And now we take up, we make another solution that contains both water as well as ethanol. Essentially, you would see that since ethanol and water are present together in a specific ratio, you would see that the overall vapor pressure of the liquids in the system, that is also going to be intermediary in between of water and ethanol. That means if ethanol is here, water is here, temperature, then in between, depending on the ratio, whether it's closer to ethanol or closer to water, you will see that the mixture is going to have intermediary values. And that's what I'm trying to show here as well. When you have molecules, in case of the solution, which have displaced the solvent molecules, essentially you're going to get, I'm showing you that here, you would see that in such a case, in such an event, in order for it to get to the same vapor pressure, greater number of molecules will be required. Or another way to say the same thing is that the vapor pressure is lesser because fewer gas molecules are present in the vapor form. And when you measure that against manometer, that difference essentially comes out to be tinier as compared to the pure solvent. So this relationship for the presence of the non-volatile solute with the vapor pressure is put together as Raoult's law. According to Raoult's law, the vapor pressure of any solution can be calculated by taking it to be in proportion with the amount of the non-volatile solute that has been added. In other words, one can say that the vapor pressure of any solution is in correlation with the amount of the solvent molecules that might be present in that particular in that particular solvent. For instance, let's say you have a water sample, okay? You have a water sample, and that water sample is being maintained at 25 degrees Celsius, all right? And it contains maybe 0.9 moles of water and perhaps 0.1 moles of the non-volatile solute, so something like glucose or sugar, non-volatile solute. So let's call that sugar. Okay, so you can hopefully see that the part which is non-volatile is not going to contribute to the vapor pressure. The only thing that can go through this evaporation process and convert from liquid phase to the gas phase is the molecules of water in this particular case. Now, if you compare this to let's say the vapor pressure of pure water at a specific temperature, in this case 25 degrees Celsius, so pure water is approximately around 23 torrs or so. And so if you had to determine the vapor pressure of the solution, you would say, well, you only have 0.9 is the mole fraction of water, and the vapor pressure of the solvent is 23. So 23 times 0.9, and so somewhere around approximately 21 torr is going to be the vapor pressure of the solution. So one can safely say that essentially if you wanted to find out how much the vapor pressure is lowered by the presence of a certain solute, you are looking at this lowering using what we refer to as the Raoult's law. So the vapor pressure lowering, which is the difference between vapor pressure of the pure solvent and the solution, this lowering is dependent on the ratio the amount of the mole fraction of the solvent that is present. So another way of writing this relationship would be, let's maybe change the color. Another way would be that if we are saying that delta P is the lowering of vapor pressure, so I'm saying that's the P naught solvent minus P solution, right? And Raoult's law is essentially P solution is equal to P solvent times chi solvent, and we know that chi solvent is 1 minus chi solute. So if you knew the mole fraction of chi solute, you can always plug in that value into the Raoult's law, and your Raoult's law will start looking like P solution is going to be equal to 1 minus chi solute times P solvent. Sometimes they also refer to it as P naught solvent just because it's pure. And so now if I solve that, I can say P solution is equal to P naught solvent minus chi solute times P naught solvent. Or you can say that solvent minus solution, so P naught solvent minus solution is going to be equal to solute, chi solute, times P naught solvent. Or the lowering that you're seeing, the delta P, is going to be equal to chi solute times the solvent. So two different ways of writing the same thing. Again, for a solution, if you were to measure just the vapor pressure of the solution, realize it would be dependent on the amount of the active or volatile solvent that is present in that given mixture. This essentially works the best when the concentrations are kept low. That means that the solute and the solvent, they really don't get a very big opportunity to interact with each other, and they have sort of similar intermolecular forces. If the intermolecular forces between the solute and the solvent are weaker than, so if the intermolecular forces between the solute and solvent are weaker than the solvent molecules alone or solute molecules alone, and so that would mean that essentially solvent molecules are not as tightly held, then the vapor pressure is going to be higher than what the Raoult's law would predict. So realize that if you have, what we mean by that is that if you have NaCl in water. So when you take NaCl in water, water is going to be able to dissociate the sodium and chloride. So if you begin with maybe 1 molar NaCl, you actually are going to end up with 1 mole of Na, and you'll have 1 mole of Cl negative. That means you're beginning with 1 mole particles, and because that NaCl is breaking down, because of the reasons that we've discussed previously, the hydration energy being greater than the lattice energy, in this case it's going to generate 2 mole particles in solution. And if these are able to interact well with the solvent particles, then that would mean that the vapor pressure overall is going to be lesser than predicted. On the other hand, if these don't interact very well with the water molecules, so that solvation is not going to take place, in that case the vapor pressure, the solvent molecules are going to be less tightly held, and so in that case the vapor pressure is going to be higher. But realize the key thing here is that if you have 1 mole of sodium chloride or any ionic salt for that matter that undergoes complete dissolution, it's going to generate 2 mole particles. If you compare that to something like maybe calcium nitrate, okay, that's going to give you 1 mole of calcium and 2 moles of nitrate. So if you begin with 1 molar particles, you're going to end up with 3 molar particles at the end of the day. And if you do the same thing with something like maybe glucose, which is a covalent compound, or urea, which is also a covalent compound, nothing's going to happen to glucose or urea. It's going to remain intact. So 1 mole particle remains 1 mole even after dissolution. The question is, what is the vapor pressure in millimeter mercury of a solution prepared by dissolving 5 grams of benzoic acid in 100 grams of ethyl alcohol at 35 degrees Celsius? The vapor pressure of pure ethyl alcohol at 35 is 100.5 millimeter mercury. So you are given that pure ethyl alcohol is 100.5 millimeter mercury. If we are able to determine chi, then we know the relationship for Raoult's law that the solution, vapor pressure of the solution, is going to be equal to P naught ethanol times chi ethanol. And so one can say that's what we have to determine. What is the vapor pressure of a solution is what we are determining. So let's determine chi. Chi of ethanol, ethanol is your solvent here, so that will be equal to the number of moles of ethanol divided by the total number of moles. So we have 100 grams, and ethanol is C2H6O, so I'm going to use 12 for carbon. I'm going to use 1 for hydrogen, 16 times 1, so that will be 24 plus 6, 30 plus 16 is 46 grams per mole is the molecular mass of, this is 46 grams per mole. And we divide that by the total number of moles. So again, for the case of benzoic acid, it's going to look like 5 grams divided by, again we do the same thing, 7 times 12 plus 6 plus 2 times 16 is going to be 32, so that's 84 plus 6 is 90 plus 32 is 122 grams per mole. So this is 122 grams per mole plus, and I'm going to say 100 grams divided by 46 again. So we are going to solve that, and I got 0.981 upon plugging in the numbers. And so right now my P solution looks like 100.5 times 0.981. So when you 0.981 times 100.5, that gives you a value 98.59 millimeter mercury. So notice when you have a solution with a non-volatile solute, it's going to cause a lowering of vapor pressure. You have dropped down from 100.5 to a 98.59, so it decreases. You can also calculate this lowering of vapor pressure by determining how much of the solute you have and multiplying that by the P naught ethanol, but that will be specifically by what amount it decreased. Here the question was, what is the vapor pressure of the solution prepared? Not the lowering, but rather the absolute values. They wanted us to calculate the 98.59 for that solution. Okay, the question is the close-up view of part of the vapor pressure curve for a pure solvent and a solution of a non-volatile solute. Which curve represents the pure solvent and which is for the solution, and why? So hopefully you can see that the solution is always going to be lower. So the way you should work is pick any temperature, the value that's higher. This value is lower. That means the red curves are always going to be for the pure solvent, and the green curve is always going to be for the solution, because as you add the non-volatile solute, essentially you take up some of those spaces, and hence the rate of evaporation is going to go down, or you can say that the vapor pressure overall for that particular solution is going to go down, because there aren't as many molecules that can get into the vapor phase from the liquid phase. Hopefully that makes sense. Let's go forward. Well, what would happen if you had a volatile solute? So what would happen if you actually had a combination of two different liquids? So both of them have the potential to convert into something volatile. How would you what would you do? How would you go about it? So realize that since in this case both of the components are going to be volatile, essentially both of those are going to contribute towards the overall pressure, and you can write down that the pressure of let's say a component, that's going to be dependent on the vapor pressure of that component, and the B component likewise is going to decide what the overall effect is for that particular or due to that particular component. So one can safely say that the total pressure seen in this case is going to be a combination of the pressure exerted by A times the mole fraction plus the pressure exerted by B times the mole fraction. And so the total, the P total, should be a value which should be intermediate of the two numbers that you would see for A and B. The question is that this is a close-up view of part of the vapor pressure curves for two liquids and a mixture of the two. Which curve represents the mixture? Like we were saying, that the mixture is going to be in between the two, so it's going to be this green one, which will be due to the presence of the volatile solute this time. So you can perhaps envision something like ethanol when mixed with water, and the mixture essentially is going to be this green curve, which will decide, or which will be dependent on the amounts of the ethanol and water that are present in that mixture. Okay, the question this hour is, what is the vapor pressure of a solution prepared by dissolving 25 grams of ethyl alcohol in 100 grams of water at 25 degrees Celsius? Vapor pressure of pure water is 23. Vapor pressure of ethyl alcohol is 61.2 millimeter mercury at 25 degrees Celsius. So what they're asking is that now you have to determine the vapor pressure, and it's a combination of two things. You have ethyl alcohol and you have water. You have water, H2O. The P naught numbers are given. For ethyl alcohol, it's 61.2. And for water is 23.8. The chi for ethanol is going to be, since we have 25 grams, so we are going to first calculate the number of moles. So again, 46 is the molar mass of ethanol because it's C2H5OH. You can plug in the numbers. We just use that number, so I'm going to go ahead and continue to use that. 46 plus 100 divided by 18. 18 is the molar mass of water because it's H2O, 16 plus 2. And we will do the same thing over here. 25.46 plus 100 over 18. And when you solve, you get a value 27.1 millimeter mercury. The one thing that I really want to, drive across here is, notice the numbers that you used. You started with 100 grams of water and 25 grams of ethyl alcohol. So in terms of even the number of moles, the moles of water came out to be like 5.55 out of the total 6.09 moles. That means the amount of water is greater, and that means that your overall values for the vapor pressure should also be closer to that of water than of ethyl alcohol. So one can say that if ethyl alcohol was here and water was here, maybe I can color code that. Water was here, H2O. Ethyl alcohol was here, ETOH. The mixture, this kind of a mixture, is going to look similar to water, just a little bit more, because we have greater amount of water in the system as compared to ethyl alcohol. Of course, we are plotting pressure versus temperature.